Hello, in this video I will go over the concept of moment of a couple and we discuss what is a couple. A couple are two parallel forces, so they're parallel, with same magnitude but opposite directions. That are separated by a perpendicular distance d. So there are four conditions. They need to be parallel, have same magnitude, opposite direction, and they're separated by a perpendicular distance d. So moment of a couple, magnitude of moment of a couple is simply FD. Magnitude of one of them, and perpendicular distance between forces. Moment of a couple is a moment, so it is a vector. And once it has a vector, it has magnitude and it has a direction. The direction of it still identified by right hand rule. So I'm curling my fingers in the direction of rotation that these two are going to create. And I always tell my students, just assume or imagine a steering wheel of a vehicle or a bicycle in your head. And think about if you apply these two forces that you are seeing here, equal and opposite direction, which way it's rotating, which way you are creating the rotation. Curl your fingers that way and your moment, the direction of moment is same as direction of your thumb. So it is a vector. We can of course show it by vector notation as well. Moment of a couple is simply R cross F, very similar to moment of a point, but you gotta pay attention. Not about a specific point. It's about nowhere. It doesn't matter. There's no point. It's just two forces and a distance, and that's all it matters. Remember, the distance starts from one force to another. So it can be about any arbitrary point you want. Doesn't matter at all. Or you can think of it as it's about no specific point. So both of them are correct. It's about any arbitrary point you want or about no specific point. I usually like to say it's about no point. Position vector is from one force from line of action of minus F here, I should say, to line of action of F. So you always go to this force. You start from the one that you are not including here and you go to the one that you're putting here. That's the direction of your position vector. And again, it's from anywhere on the line of action. Anywhere on the line of action. Okay? And here's a little proof for you. So proof that this is proof of position vector from any point on line of action of 1 to any point on line of action of the other one. So let's assume I said it's about null point, but let's just take arbitrary point O and find moment of those two forces about point O, and find resultant. Let's use resultant moment of F and minus F about that arbitrary point O. So my moment in vector form is going to be from O to any point on line of action, right? Let's call that RA, cross minus F, RB from O to any point on line of action or off line of action in B. So let's rearrange this. So it's kind of opposite of distributive law. I can write this as RB minus RA cross F. Okay, so you got to go way back to where we started looking at operations of vectors. So, and if you look at this triangle here, I can see that RA plus R equals RB, the triangle rule. So let's rearrange this. Then R equals RB minus RA. This is exactly what I have here. So R cross F. And again, remember, these position vectors were to any point on line of action. So this is any point line of action. Any point line of action. So for any point that you take on line of action, this equation is valid and you can use it. Let's talk about equivalent couples. We call two couples equivalent if have the same magnitude, same direction, same tendency to cause rotation in same direction, and both of them lie in a parallel plane. So let's look at this figure first. The man is opening a huge valve. The first one let's see, let's call this 1. It's a couple because they are parallel, same magnitude, opposite direction, and they're separated by a distance. So they have all conditions of being called a couple. So magnitude of it, M1, is magnitude of one of them multiplied by distance between them, 0.4 meters. And I'm glad that you're doing this because I get a chance to explain the units on the moment. Because moment is force multiplied by a distance, the units are force, distance. So the magnitude of this couple is 12 Newton meters. Okay, figure 2. The force is now 40 newtons. The distance between is 0.3 meters. So this is also 12 Newton meters. They're parallel, so they have the same magnitude. And if we use right hand rule, the moment is kind of going in the screen, going perpendicular in the board, and that's the direction. So same direction, so we can say 1 and 2 are equivalent couples. Okay, and one thing I want to mention again, moment of a couple is about, for both of these, about no specific point. I know it's kind of hard to imagine, but a good example that I tell my students is if I pin this this valve here, the moment and the couple magnitude, direction, everything is the same, is exactly the same, doesn't matter, P1. So let's move it and pin it about this point, meaning I remove this bolt here, remove this here, now I'm making an axis right there. The whole rotation, the magnitude of the couple and the direction of the moments is still the same. So as you can see, it doesn't depend on any point that you make an axis or pin this wheel. It still has the same magnitude and same sense of rotation. Why is this important? Because we call moment of a couple a free vector, because it does not depend on any point, any specific point. So let's look here. Look at A and B. So for A and B, you can take a couple. These two are parallel, same plane, distance d, opposite direction, same magnitude. So you can say, you can take these two and replace it by an equivalent moment. So this is represented by a vector with a magnitude and direction equal to the moment of the couple. It is a free vector. A free vector. This is super important because we're going to use it and you're going to see in examples. It's a free vector, does not depend on any point. So it doesn't matter if I move it around. Means you can absolutely move it around, as long as you don't mess the magnitude or direction. Now you can see in the C, they just moved it and put it at O. So couple vectors, still a vector, meaning it has something I, something J, something K. So, and that's what figure D is showing. That moment of a couple is still a vector and it still has its mx, mz, and my. So we're going to use this free vector capability or feature of it and simplify some of the systems. As you can see here, this system can be turned into what you're seeing on the right, because it's a free vector without missing the direction or magnitude of it. I moved it and put it at the same point, so I can just use a simple addition of the vectors and find the equivalent or resultant moment. In this case, the resultant moment is simply same as before. This is something that we've had before, or you can just say moment of couples, just addition of moment of couples. Watch the next video for multiple examples on moment of a couple that I've done for you guys. Thank you.